chapter 17 is not in your textbook. How fun is that? But this topic is in the course outline. So I meant to write some notes, and I forgot. I will write notes and post them for you. So, and this lecture will also be posted on YouTube. So we're just going to cover some highlights of chapter 17. This will not be on the exam on Monday, but there will be a little bit on the final.
Do you have any homework from this chapter, since it's not in the book?
Pardon me?
Do you have any homework from this chapter, since it's not in the book?
That's a good question. I don't know what to do about homework. Well, I'll think about that later. That's just too much for today.
The last chapter.
I really like to include this chapter because it explains a lot of things. So, how do chemical reactions occur? One way of understanding this is called the collision model. So, in order for molecules to react, they have to collide with each other. They have to run into each other. If they don't even come in contact with each other, they cannot react. That makes sense, right? In order for two people to fall in love, to have a chemical reaction, they have to actually meet each other. And the rate of a chemical reaction is going to depend on the concentrations of the reactants and on the temperature. And it would be really great if I could remember where these slides are going, but I can't, so I'll just keep talking. Let's look at this picture. So here we have two BRNO molecules, and they're approaching each other at high speed. They collide, and a reaction occurs. These are covalent compounds. Bromine, nitrogen, and oxygen are bonded to each other. In order for new bonds to form, the old bonds have to break. Does that make sense? If you've got two Lego structures and you're going to make something new out of it, you have to take the old ones apart first. That requires some energy. So these guys run into each other. If they collide with enough energy, then some of these bonds will break, which will allow new bonds to form. So the bromine-nitrogen bond will break from the force of collision on both of these, and then we'll get a new bromine-bromine bond that's formed. And then here we have our products. This is just an illustration. You don't need to know what these are named. We haven't learned that. You don't need to know that these react in that way. But how would concentration of reactants affect the rate of this reaction, of how fast the reaction proceeds? If there is a higher concentration of reactants, what will that do to the number of collisions? Will there be more collisions? Yeah. Because you think of a room, and we've got, 15 people in here maybe. If we had 100 people in here and we're walking around, would there be more collisions? There would be. We're walking around, we're going to bump into each other more. More collisions, more reaction. It will happen faster. What about the temperature? What do molecules do at higher temperatures?
Move faster.
They move faster. So if we took the 15 people in this room and instead of walking around like we do during lab, what if we ran? Would we run into each other? Yes, a lot. So there would be more collisions. And what about the energy of those collisions? It'd be higher because now they're running at each other with more force. So more of those collisions are going to have enough energy to be successful. You can have a collision between two molecules, but if there's not enough energy there to break the existing bonds, nothing's going to happen. Like you could meet the person who is your future significant other, but if you were both just out of it, you may not even notice that person, right? There's no spark, nothing happened, and then maybe 2 years later you run into each other again under better circumstances, and all of a sudden, oh, wow, So energy has to have enough energy, they have to collide. And so if you increase the concentration or you increase the temperature, it'll happen faster. Okay, see, concentration increases the rate because more molecules leads to more collisions. It's crowded. The temperature increases because higher temperatures, higher speeds, so the collisions are higher in energy, and you have more collisions, and so you get a faster reaction. there's something called activation energy. I talked about there has to be enough energy in this example, for this nitrogen-bromine bond to be broken. And that's called an activation energy. And if we look at an energy diagram, there's a hump here. This reminds me of playing miniature golf and how they always have those annoying little humps in the miniature golf course, right? And so here you are playing miniature golf, and you've got some crazy hair thing going on. Didn't mean to do that. Right? And here's your golf club. And you have to hit the ball with enough force to get it up and over the hump, right? If you don't hit it hard enough, it goes partway up and then it rolls back down. And you don't get the ball into the hole, right? There has to be enough energy. And so this hump here, this is the activation energy. So in order for the reaction to occur, when those molecules collide, they have to have enough energy to get up and over that hump. If they've got more energy, that's fine. But if they bump into each other with less energy, nothing happens. Once they get up here, then it's just all downhill from there. But activation energy. So, a catalyst. Catalyst is a word that we use in everyday life. You know, you might refer to someone at work and say, well, you know, he was a real catalyst for change. He made things a lot better around here. Well, catalyst is a chemistry term, actually. And a catalyst is a substance that speeds up a reaction. But it does so without being consumed. So we use a catalyst, and yet it doesn't actually, it's not one of the reactants, and it doesn't get tied up into the products. Enzymes are biological catalysts. How does a catalyst work? Well, a catalyst works by providing a pathway, an alternate pathway that's lower in energy. So now for these reactants, when they collide, they only have to have this much energy instead of all the way up here. It's like lowering the hump. So another analogy I have, I've got space here, I'll give you another bad drawing. You like my bad drawings? Okay, so here's a fence. Okay, and here's the little line of kindergartners, and I don't know, they're on some weird field trip, and they have to climb over the fence. Can the kindergartners climb over the fence? Yes, they can. But it's going to be kind of slow, isn't it? For whatever reason, they can only go over one at a time, and it's going to be a while, because you've got, you know, this whole horde of kindergartners. You got to wait for them all to climb over the fence. There's this activation energy. Okay, there's this barrier they have to get over. Now, what if you put a teacher in here who takes the child and lifts them up and over the fence? Strong teacher. They're going to go over faster now, right? Does the teacher really involved in the reaction? No, the teacher's just making it easier for it to happen. The catalyst makes it easier for the reaction to happen by lowering the activation energy. And that's what enzymes do in your body. So your body is, the more you study your body, the more amazing it is. Okay, it's this giant chemical factory, and there's all these chemical reactions occurring. And how does your body tell them, yes, we want this one to happen now, and no, okay, that was enough, now stop? How does it control all of this? Well, enzymes are one way that it controls it. The other thing is that a lot of the reactions that occur in your body, the rate is actually very, very slow. Can you just heat up your body to make the reaction happen faster? No, because a lot of biological molecules are very temperature sensitive, and your body controls your temperature very closely, 37 degrees Celsius. And so you know that it's 98.6 Fahrenheit. You know that if it gets above about 106, you're in trouble, right? And if it gets too low, you're also in trouble. So your body regulates that very tightly. So it can't use temperature to speed things up, and it can't really change the concentration to speed things up, and so it uses enzymes. And so you make the enzyme, and that lowers the activation energy, and the reaction can proceed faster. So if you're missing enzymes, then you have trouble. Question?
Because you're talking about the body stuff.
Tangents are good. I love tangents.
Can like a biological enzyme with the nuts,
Mm-hmm.
can it lower like the energy needed to create like an action potential for certain things? The same way as it does for like chemical reaction?
I am not up to speed on action potentials. Yeah. I have a vague remembrance of what they are, but I don't use them, and so I relegated those to a dusty closet in the back of my brain. And we're not going into dusty closets today. It's a scary, scary place.
Is that
But
what
probably.
the catalytic converter is for in a car? That it makes it run more efficiently in...
What a catalytic converter in your car does is it takes the products of the combustion that are undesirable, and it catalyzes a reaction of them into things that are less undesirable. So it does not make your car work more efficiently, but it makes the substances coming out of your car in the exhaust less bad, less harmful. Harmful is a much fancier word. It does that by lowering the activation energy, yes. Yep. I'm just going to run this all together. One video, one long, crazy video. So equilibrium. Equilibrium's cool. An equilibrium is the exact balancing of two processes that are opposite of each other. So if we think about a flask here with a stopper on it. Flask with a stopper on it. This, we'll pretend that's water. So the water is evaporating. The water evaporates, and then you have water molecules in the gas state, and they will collide with the water and condense. So we have evaporation and condensation. Those are opposites of each other. And if you allow this flask to sit for a while, we'll come to the point where the rate of evaporation and the rate of condensation are the same. And so we have an equilibrium. An equilibrium is a dynamic state. But looking at it, it doesn't look like it's dynamic, because it looks like the concentrations of reactants and products are staying the same. When they are, but they're actually switching places. It's a little bit like, maybe an airport. Busy airport in the middle of the day. So at noon or at 2 o'clock, the number of people in the airport is the same, roughly. Is it all the same people? No. Because some of the workers may have left and new workers came, airplanes arrived, airplanes departed. There's this constant back and forth, people arriving and people departing. So it's always different people, but the number of them is the same. So that's what happens in a chemical equilibrium. So here, if you put the liquid in here, let's call it water because it's more convenient. So if you put water in here, and initially there's nothing in the gas state, what will happen is the water will begin to evaporate. So there's evaporation. There can't be any condensation because there's no water molecules up there to condense. So initially we have this rate of evaporation. The rate of evaporation depends on the temperature of the water only. So some evaporation occurs, and we get some water molecules now in the gas state. These then can begin to condense. As we get more and more gas state molecules, the rate of condensation will increase, because the more particles you have up here, the more will eventually collide. Does that make sense? If you have a whole bunch of gas molecules up here, more of them will collide with the surface and condense. So initially we have this rate of evaporation, and that rate of evaporation stays constant the whole time. The rate of condensation is very slow at the beginning, and then it gets faster and faster as we get more. Eventually what happens is the rate of evaporation is equal to the rate of condensation. And at that point, we've reached a dynamic equilibrium where we have things evaporating and things condensing at the same time, different molecules. It's a little bit like two kids standing on opposite sides of, say, the tennis net, and they each have 10 balls. And they start throwing, well, actually, initially there's 10 balls on 20 balls, let's say 20 balls, I don't know why. 20 balls on one side of the net, one kid on each side. And the kid starts throwing balls over the net, okay? Until there are balls on the other side of the net, the kid on the other side can't put any back over, right? As there get to be more and more balls over there, it's easier for him to run and get them, and he starts throwing them back. And eventually, you'll get to a point where they're each throwing balls across the net as fast as they can, and it will be equal. And so if you looked at any given time, the number of balls on each side of the net would be constant. I think we need a bad picture. It's time for a bad picture. So, yeah. So here's the tennis net. It kind of looks like a tennis net, right? And you've got a big kid over here. This is James. And you've got a little kid over here. That's Andrew. Isn't he cute? It's a good thing. He sure is trouble. Ooh, those are really big tennis balls. Maybe make those a little more proportional. Okay, so initially all the tennis balls are on one side. And Andrew starts throwing them over. And then James is throwing them back. Now, James is better at throwing them back than Andrew is, because he's just bigger and faster. He's more coordinated. So what's going to happen eventually is we're going to end up where we kind of get a balance. And an equilibrium does not mean that it's the same on both sides, just that the rate of going in each direction is the same. And so what do we have? 2, 4, 6 balls on Andrew's side and 3 on James's. They're throwing balls over the net, but it's always 3 on James's and 6 on Andrew's, because James can get them back a little faster than Andrew can. Does that make sense? So an equilibrium does not mean that the concentrations are equal. It just means that they aren't changing. So this is kind of a neat way to say it. For a chemical equilibrium, on the molecular level, there is frantic activity. Molecules are reacting. They're either evaporating and condensing, or they're going in the forward reaction and the reverse reaction. It's not a static situation where everything's just frozen. It's highly dynamic. But we can't see that happening. What we see, if we can see anything relevant to this, is that it looks like it's the same. So macroscopically, on the level that we can see, it is static. But microscopically, it's dynamic, it's changing. What is this slide? Well, let's read the captions. Equal numbers of moles of water and carbon monoxide are mixed in a closed container. Okay, so this is the carbon monoxide and this is the water. And then a reaction begins to occur, forming hydrogen gas and carbon dioxide gas. As that continues, more reactants are changed to products. But we get to a point where, even though time continues to pass, the numbers of reactant and product molecules are the same as they were before. So if we measured the concentrations of all these things, they're not changing anymore. Does that mean there's no activity going on? No, there's still activity going on. Because what do we have going on here? Let's write an equation. So we've got water and carbon monoxide, and it says we're forming hydrogen and carbon dioxide. So this is going in both ways. It's an equilibrium. The reaction can go forwards and it can go backwards. It's like throwing balls over a net. This is in the gas state.
It wouldn't work with a precipitate. It wouldn't be going back and forth.
It actually does work with a precipitate because even something that we consider to be insoluble is very, very slightly soluble. And so what happened, like, let's say we had a saturated solution. That's a little easier to understand. So you'd added enough sodium chloride so that you've saturated it. No more will dissolve. And you might look at that and say, well, yeah, there we go. That's just nothing happening there. If you wait for weeks and you come back, you may notice that the crystals of sodium chloride on the bottom of that beaker are not the same size that they were before. They will probably have grown because there's this constant dissolving and then redepositing. And as it does that, it tends to form bigger crystals. And so a lot of things are actually an equilibrium, but we just can't see the effects of that. So this is a graph that shows what's going on here. So this is reaction rate. So high on the y-axis means a high reaction rate, and this is low. Down here it starts at 0. So the blue line is the forward reaction, the water and the carbon monoxide reacting, and the reverse reaction is the red, hydrogen and carbon dioxide reacting. So initially, there's no hydrogen and no carbon dioxide, so the reverse reaction cannot happen at all, right? And the concentration of the reactants, water and carbon dioxide, is the highest that it's going to be. As the forward reaction proceeds, the concentration of the reactants goes down. Does that make sense? Because when water reacts with carbon dioxide, it forms these, and now we have less water and less carbon monoxide. And the concentration of the reactants affected the rate. When the room is less crowded, there will be fewer collisions. So as we're going down, as time passes, this reaction rate is going to go down because the concentrations of the reactants is going down. The reverse reaction rate will increase. Initially, there were no products, and so the reverse reaction could not occur. But as we get more and more product, that reaction rate will increase. And eventually we'll come to a point where the rate of forward reaction is the same as the rate of the reverse reaction. And that's where you have the equilibrium. Does that make sense? So the concentrations reach levels where the rate of the forward reaction equals the rate of the reverse reaction. So let's do some thinking exercises. So here we're going to stay with that same reaction, the water and carbon monoxide reacting to form hydrogen and carbon dioxide. If we add more water to the flask, how does the concentration of each chemical compare to its original concentration after the equilibrium is reestablished? So let me explain that. So we put water and carbon monoxide in that jar, and we allowed it to sit, and it came to equilibrium, where we've got forward reaction and reverse reaction going on, and everything's equal. Now it's saying, what happens if you add more water? Adding more water, is that going to change the rate of the forward reaction? Does the concentration of the reactants affect the rate of the reaction? Yeah, it does. So if we increase the concentration of this, even if we don't change this one, if we increase the concentration of the water, the forward reaction is going to go faster. So it's going to go faster, but then it's going to slow down again as this concentration decreases as the reaction proceeds. Remember on that graph we had, let's draw it here. So we had the initial reaction was decreasing until it came to this level point, and the reverse reaction came up and met it. So if we speed up the forward reaction, how's that going to affect the concentrations of these chemicals? Is the hydrogen and the carbon dioxide, is that going to be higher afterwards or lower than it was before we added the H2O? It should be higher, right? Because when we add H2O, we increase the forward reaction, and so the equilibrium tips this way because we can make more product faster. So this would be like taking this and raising it up. Let's do another one. What if we added more hydrogen to the flask? Which reaction would that speed up? The reverse reaction. So that would cause the reverse reaction to go faster, and it would cause the water and the carbon monoxide concentrations to go up. Does that make sense? Yes? No? No? So we have two reactions going on here. That's not what I meant to do. So we've got forward. The rate of the forward reaction is going to depend on the concentrations of the water and the carbon dioxide gas. The rate of the reverse reaction is going to depend on the concentration of the hydrogen and the carbon dioxide. Does that make sense?
Yeah.
Okay. So if we increase this concentration, that causes this reaction to go faster.
I was still looking at the H2O, the H2 on the H2O.
Oh, okay.
I was going, wow.
Yeah. So this is like with James and Andrew throwing tennis balls. So if you gave, heaven forbid, if you gave Andrew an energy drink and increased his reaction rate, okay, now we're going to find out that there's an increase in the number of balls on James's side because Andrew is suddenly just more energetic, which that's very scary because he's so energetic to start with. But he's going to be throwing balls more efficiently over. Okay. Another way to think of it, which would be a lot better because it doesn't involve giving him caffeine or anything. What if, he started out, what did we say? We had 3, we only had 9 balls. What if we added 10 balls? No, we can't add another kid. Added 10 balls to Andrew's side and let the equilibrium reestablish itself. And then we look at James's side of the net. Is he going to have more balls over there or fewer? He's going to have more because we're going to establish the same sort of a balance back and forth. But now there were more balls that we put on that side. So Andrew's initial rate is going to be faster because there's just so many more balls to get to. And so he can get them over faster, and then James is going to end up with more. Does that make sense?
Could you add either the CO or the CO2 to
Yes.
the same thing? That would apply. Okay.
Yeah, so if you added CO2 instead of H2O, the same thing would happen. Or if you added both of them, the same thing would happen. And this section is for next Wednesday.